All right. The first announcement, I guess the only announcement, is that Quiz 3 is available on Canvas. You have 3 days to work on it at any time. As soon as you start working on it, you have 20 minutes uh, to finish the quiz. Okay, so remember to remember to do that. Remember. Okay. Um, we'll go over today's lab. Ampere's law. Let me share my screen. We'll go to Canvas and you'll see this. It's only worth 60 points. I've from my many other labs, I've heard that this is one of the more difficult um, labs so far during the semester. So I'll leave that as for each of you to determine. Let me go into the directions. Also, before I get like too into my intro, um, my internet's been cutting in and out, so I might be disappearing a couple times. Just to hang tight if I do. Okay, so for the instructions, remember to always include your introduction at the top. There's now this new space for it. Um, we're going to be doing all of our work on Pivot Interactives. So you'd head over there and log in, and we're going to be watching just like a series of videos. For this first one, there's going to be this track. Actually, before, let me just head over, do that. So when you log into Pivot, there's going to be these two parts. So lab 8, part 1, that's going to be for half of today's lab, part 2 for the other half. So in part 1, it's going to look a little different getting there, but as soon as you do, you'll see this. Um, what we're looking at is a tabletop where the so we're looking down on the tabletop. There are 4 compasses that are elevated a bit above the tabletop. They're sitting on this wooden track with a gap inside of it. Down below, much farther below, is an ammeter. This is going to be something that measures the current flowing in this green wire that's going to be going right through the gap. And so up here near the top, you can imagine that's kind of right near where our eyes are as we look down. So we're looking down, this is going straight through. There's also a little black marking. There's a little marking on the green wire. So at that marking, that's going to be the same height as the compasses on this track. Something that might be helpful in a couple of these videos. Okay, so I believe in the pre-lab, he sort of showed you what they're going to be doing, but you're going to be predicting what they're going to do before you watch the video. So in the instructions, says it says in a couple different places it says predict what will happen. And whenever it says predict, I'm not going to grade how you predict it. It could be completely wrong. That's okay. So whatever your predictions are, draw what would happen. There's going to be quite a few drawings for these first parts. So include a sketch of the compasses with their needle directions. So I want to see a sketch, have it arranged how it matches the video. I want, labeling. So it could be like an arrow or like put an N for the north side of the compass. And I also want to see um, where the wire is and which direction the current's flowing in the wire. I believe from the pre-lab, the current is flowing towards us. So it's going to be going up the wire or sort of towards towards us. Okay, so that's the first part. The second part is analyzing the four compasses that are around the wire, like this. So that's going to be just in the same sort of page. Scroll down to four compasses in a plane right here. Watch that video. You're going to predict what will happen and observe what does happen. Try to explain it. And then the third part, this first section, there's going to be a person that slides in this compass near this green wire. Let me go over here, and it's going to be this third video down here at the bottom. You can see on the meter 0, so there's no current flowing in the wire right now. Let me play the video just for a little bit right here. And this person will slide in this plastic compass. Let me stop it right there. And you see that the compass, the needles are pointing, the red side is pointing north. It's aligned with Earth's magnetic field. That's the same with all of these. See, they're all pointing the same direction because they're lined up with Earth's magnetic field. This is just everywhere in space around Earth. And all of these compasses are just sort of orienting themselves to align with that. Now, what's going to happen is you're going to change sort of the settings right here and observe what will happen to the compass needle. And we're going to take sort of some measurements. You could take distance measurements up here in the tools. You can record the distance with this ruler. So that's where the sort of marking on the wire comes in handy. So I could line up sort of a distance like this and try to measure that way. Remember, these are centimeters. Okay, so we could get a distance that way. We could also figure out a deflection angle. So maybe we want to, let's measure the angle of this deflection right now. So let's bring out this digital compass. That's just what I'm going to call this tool. Digital compass. And a way to help us measure, we're going to need this, click on this line up here, this reference line. Let's put that the best we can, lining it up with the center of the needle. And then we place the digital compass on top of the plastic compass. And we line the centers up like that. Now we can measure the amount of deflection of the needle. You can see on the right side, it's at 0. So there's 0 deflection. Say, for example, in one of your videos, in one of these sort of different versions, the needle is sort of tilting up a bit like this. This is just an example. And you see it would be following what the needle would look like. But having like this, there we go, I would then be able to measure this small amount of deflection. So it went from going completely horizontal to up just a tiny amount. So this would be, if this is 350, it wouldn't be an angle of 350 degrees. It would only be an angle of 10 degrees. You imagine this is 360. You have to subtract a difference. Okay. So that's how we're going to do this part. With those measurements that you get, you're going to go and take them and you can graph them. You could graph them in Excel if you want, or down here at the bottom, there's a graphing tool for us to use. Okay, let me go back to the instructions. Okay, so that, we're going to graph. All right. Then we're going to move on to this second part. And the second part could be seen as the more difficult part of the lab. Let's head over there. So it's going to be in that second link in Pivot. So I'm going to have to go back and go to part 2. Okay. So we're going to see this arrangement. And what we have is a battery, a scale. This is like a this is a force scale. So whatever's on here is just measuring a force. And we have this sort of, setup above it. There's this wire and a magnet. Let me go down to the video. It's a bit clearer to see. So on the battery, the terminals are clearly labeled. So there's a positive and a negative. And throughout this lab, we're going to use conventional current. So not the electron flow current. We're going to assume positive current. So coming out of the positive terminal and traveling down this way. So coming out of the positive, moving this way, and it would travel through this wire. If you look at this wire, it's connected to a wooden board. So it's sort of like just pinned down to this wooden board, and that wooden board is connected to this scale. So if the wire is forced downward, this scale will increase and it'll read as forced downward. There's also an option where maybe the wire is forced upward. There'd be a sort of upward force, it would lift it up, and the scale would, go backwards. But what we're going to do is look at this. We could see that here is the flow. The current's going to come out of here, go through the wire, go this way through the wire, and back down and return to the battery when it's connected. We're going to see what does this flowing current, how does it react by being near this magnet. There's this magnet just sort of stationary that's not moving in the background. There's this yellow sticker. Can't quite see it that well. There's an S on it. S for the South Pole. Let me switch to the other one. We could change sort of the current direction, and we could change which side of the magnet is showing. So if I go to out like this, go to load, now you can see that's a red sticker that has an N for north. This is the north side of the magnet. I'll go over a bit of this in my notes in a minute. Okay, so we could change which side of the magnet is showing, and we could also change which side the terminals are connected. So we could change the current direction. So instead of positive being on the left, we could swap those. So let's go like this, current direction. So now positive is on the right. So you're going to use this as a practice tool. You're going to see what happens in all of these combinations. North side is facing, and then the current is going this way. What happens when the current goes that way? Let's for example, let's do this one. So the positive side is over here. Let me play it. So it's right before he connects it. So positive, it's going to flow down, and it's going to go this way through the wire and return to the battery. And the north side of the magnet is showing. Let's see what happens to the scale or to the wire. Is it forced down or is it forced up? You see it was forced up for a minute there. Then they let it go and it resets. So you're going to use this as your tool to sort of figure out what is what, all of these different combinations. Then down at the bottom, down here, this is where the tricky part comes in. You're going to have a set of unknown questions. So question 1, it might ask you, which terminal is which? They're not labeled. How can you tell? Well, from that practice from up in the first section. So there's that one. There are some of these. We're going to be doing, all of these sort of mysteries you got to investigate. Some of them might not have the terminals labeled. Some of them might not have the magnet polarity labeled. That's all for you to investigate. Okay, and sort of in the middle here, I skipped over, that's some right-hand rule practice. There's this way that they use right here for right-hand rule. I know that you might have a different way from your lecture, something about your palm side facing somewhere. Uh, whichever way you're comfortable with, you just try to take that and map it to this, and you can use that to practice. So in this way, currents is the index finger, middle finger is the magnetic field direction, and then your thumb is the force, magnetic force. Okay, there's that. And then at the very, very end, part 3, that's where it's just a final bit of drawings. Same type of situation where there's a plastic compass sitting on a table, and we're looking down at the table. In this case, there's a current carrying wire. This line is a wire, and it's on top of the compass. So what's going to happen to the compass needle? Which direction is it going to point? So you're going to draw the compass needle on all of these diagrams and make sure they're labeled so I know which side is which. Okay, so this first case is the wires on top of the compass. Second case over here, the compass is above the wire. And this is to the side. This is to a different sort of orientation. That's the wire is going sort of from our eye into the page or into the table. At the very end, conclusion and your feedback. So pretty lengthy, or it's not lengthy, it's pretty conceptually challenging, I've seen. Are there any questions on this? Well, I guess before I say that, what I'm looking for today is I want to see just one set of drawings from any of these parts. So from part 1, any of these drawings, or you could do this 1.2. There's a lot of drawings in this first section, and I'm only looking to see that you guys got some step on the drawings. So that's all I'm looking for today. Let me head over and do the notes. If you have a question, just say so. Okay. All right. So we are going over Ampere's law. I'm going to put Ampere's law at the top, but I'm not going to actually get to that until the very end. I'm going to do just sort of a basic magnetism notes today. So, let's talk about uh, permanent magnets. Let's go from the ground up. So, permanent magnets. What is a permanent magnet? Let's do a little bar magnet like this. Okay, so for every magnet, there is going to be a north and a south side, or polarity. Sometimes they're just referred to as polarity. And these could have been, we could have gave them a positive, negative. We could have said red or blue. We just decided to call it north and south. From observation, we've seen that the north side of a magnet tends to have a magnetic field that comes out like this. And from observation, we've seen the other side tends to have the magnetic field that goes inward. Now, these lines don't technically stop right here how I have them. They actually loop in on themselves. So let me actually complete this drawing. So like that. It's symmetric like that. And that looks pretty good. This second one would loop in also, but it would be a little too big for my page. So we'll go like that. All right. Now, why does this, solid thing have this magnetic field around it? Where's that coming from? You can see there's sort of like this cycle that's going on. So if I was to follow one of these loops all the way around, it goes like this, all the way around, back into the magnet like that. And the other side, it would go like this, like that. But so that makes my drawing a bit messy. Let me get rid of those. So we can see this sort of, direction. There's a flow inside of the magnet even. It's going that way. This is called the magnetic moment of the magnet. We're not talking about this specifically today. It would have been like an in-person lab. We would have done something on this. So I'm just gonna. I don't even need to put that symbol down because we're not gonna discuss it that much. But what it is, why is there just this sort of direction inside of this solid piece of metal? Why have this field around this? It's just sitting on my desk. Let me break off a piece of this magnet. Let me take a little chunk. I'm just going to take that little circle and I'm going to zoom in. That. And let's sort of like zoom in on this just magnetic piece of metal and look at its molecular structure. So it's a bit of metal, and it's made of a lot of tiny little pieces of metal that are melted together to sort of like form one coherent thing. But it's made of sort of these blobs that have been melted together. So I'm just going to draw them really sort of big like this. And these are called domains. Just sort of, random shaped things that have been melted together. This is molecular structure, very, very tiny. Let's look even farther. Let's look at the atomic structure of this magnet. So, looking in a bit more, I'm going to zoom in a bit more, and just to, simplify everything, I don't want to draw like all of the protons. I'm just going to say the nucleus is just one big positive thing. And I'm just going to make this one, I'm just going to make this one electron. Like that. So I'm just looking at a single atom. Um, Normally, the electrons, they're the ones that are moving throughout the atom. So it would technically be like, buzzing around all over the place. And that's the electron cloud. And we can't really track it. But we can sort of measure that there's this sort of averaging direction that it goes. So it kind of goes that way, it kind of loops around, it kind of comes back like that. And it's this loop that it makes. It's making this loop. It's this moving charge that's moving in a circle around this, central uh, charge that creates this magnetic field. And this is, we're using a right-hand rule here. We would see that in this case, I believe it would be, there would be an upward magnetic field. Well, this would technically be the magnetic moment of the atom. All of this is, I want to keep this very general. You could just think of it as there's this strong magnetic direction that's made just from the atom. So on the atom itself, it has this direction that it's pointing. And if we take that, idea of the atom, it has a, strong tendency to have a magnetic field that points in a specific direction. Let's go back to these domains. And let's say um, that's one atom, and it's pointing that way. And all of the other atoms in this domain are also pointing that way. Okay, so they're all lined up. In a, regular piece of metal, piece of iron you see on the ground, it's neutral. It's neutral because all of these domains are facing in opposite directions. So you can see that the domains from this one, this blob, or the direction from that domain cancels that domain, and it has all of these, millions of different directions canceling each other. But in a magnet, all of the domains are aligned, or all of the directions of the magnetic moments are all pointing the same direction. And when they are all pointing the same direction, then zooming back out even more to the magnet itself, we get this overwhelmingly strong magnetic field, magnetic moment direction that way. And that creates this permanent magnet that you could leave on my desk and will be magnetic anytime I come back to it. It's because of the atomic structure. Okay, so that was just very general thing on permanent magnets. Let me do some vector notation. So the magnetic field, or commonly you could just say B. So the symbol for the magnetic field is B. So B field. I could just say vectors in general, but we need to consider these vectors in 3 dimensions. That's what I'm going to do right now. So let's look at this, there could be a magnetic field pointing that way, and let's label it like that. Or it could be off at some, obscure angle like that. But since magnetism is, we can't ignore how 3-dimensional it is. We need to be familiar with magnetic fields that point at us, or vectors that point at us or away from us. So we have to make the notation of a vector pointing towards us and away from us. So something that's going away from us, we could denote as an X. Say that. So away from us and towards us would be just a dot or a circle. Okay, let's do into page. And this would be sort of into the page or into your computer screen. It's going directly into it. This is directly out of the page. Okay. An easy way to remember that is thinking of a bow and arrow. So if you sort of pull back an arrow and sort of let the arrow go, it'll fly away from you, and you'll see the tail feathers, the fletching on the back of it, and that resembles this X as the arrow goes away from you. Now, if someone shoots an arrow at you, you're seeing the arrow tip, the point of it, and it's coming at you. You only see a dot as it comes towards you. Okay, so we need to be a bit more familiar and comfortable with this because it's hard to ignore how 3-dimensional everything is in the real life. Okay. I think I'll do one more big example. Shrink. That's enough room. Let me do let's go like this. Let me do the case of 2 parallel wires next to each other with current carrying wires. Let's first look at one wire. That's this is a wire that will be carrying a current. I'm going to label as current 1. It's going to be going up the wire. This is going to be a conventional current, so just think of this as a positive current flowing upwards. And we're going to need to know the magnetic field direction around this wire. What you can do is use the closed fist or closed right hand rule. So making like a thumbs up, and your thumb will be the current direction, and the way that your fingers wrap will be the direction of the magnetic field. So in this case, up, that means on the right side, so on the right side, it's going into the page, and on the left side, it's coming out of the page. Let me try to draw a couple loops, and then I'll represent it as dots and X's. Let me do a loop like this. So it's like that. And we have to always remember too that magnetic fields aren't just a single line like this. It's a field that expands out into space, you know, almost infinitely outward. So it's not just this one tiny little loop like this. It's going to be a collection of loops. Let me make like that. And these are perfect circles that are going around this wire. I have it off center so you can see how three-dimensional this is. But if I were to look at sort of the very edges of the wire, this path right here, that's how I can say on the right side of this wire, the field is going into the page. So that's 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 that one's not that clear. And on the left side, they're coming out of the page. So instead of drawing all of these loops over and over and over again, I'm going to put next to the wire, I'm going to put this. So into the page. So these X's would extend outward almost forever. They'd get weaker as it gets farther away. I don't need to do that many. Let me just do 3. Sure. On the left side, they're coming towards me. They'd be dots. And I'll just label these all as magnetic field. So B1. On this side, it's the same thing over here. These are vectors like that. Okay. Let's see. Let's add another wire in here. So maybe you've already seen this. You've already done like this a lot, but this is helpful for the lab. So we'll go over it again. So let's make another wire that's will have a current flowing through it. I'll call this current 2, and it's also traveling upward. So it would have the same sort of circular magnetic field flowing around it using that closed right hand rule. And it would have the same sort of, I'll do just like one loop. Has the same sort of thing flowing around it. So I'm just going to, up here on the right side, it's flowing into the page. on the left side, it's flowing out of the page towards us. I'm going to label this as magnetic field produced by current 2, so B2, like that. Okay, so just imagine these fields are expanding outwards. Now, we want to know what kind of forces are felt between these two wires. Let me slide that down. It's about there. So we know that if something is in a magnetic field, it could be forced to move in a specific direction. How can we tell how these wires will move? Well, we need to look at some specific things. Let me pull this up so I don't have to draw a hand. That and that. Okay. So let's look at this. What will be the force? Where will this second wire be forced to move? So we need to look at all of the factors acting on it. So I'm going to make a separate sort of, current up here. So it's moving upward. And what kind of magnetic field is it moving through? Now, it's not the field that it's producing, it's what field is it in. So it is in a magnetic field produced by wire 1. And that's this one over here. You imagine these x's from wire 1 are extending all the way out. And so it's feeling this inward magnetic field. I'll just put it's feeling, I'll put it over here. An inward magnetic field that's being made by current 1, like that. So we have its own current direction and the field that it's moving through. Let me get that right-hand rule thing out. So I'm going to cover this side specifically. So I2, it's moving this direction, and it's moving through this magnetic field. So I use this right-hand rule. So the current direction is up. The magnetic field direction is into the page. And then my thumb is left. So my thumb tells me which way this wire is being forced to move. So current, that's the index finger going up. Magnetic field is into the page. Your thumb is the force. Which way is it being forced to move? Being forced to move that way. Let's do the same thing for wire 1. That should be a lot simpler now that we have a handle on it. We need to see which direction is its own current going. It's going up. Which magnetic field is it moving through? So it's moving through that field produced by wire 2. It's a bunch of dots on this side of wire 2, right? I'm looking at the field produced by wire 2. So it feels it's moving through this field that has been produced by wire 2. Let me pull the thing up. So I'm covering that wire specifically so I don't look at it. So its own current is flowing up and it's moving through this field produced by wire 2. So current is up. Magnetic field is towards me. So my thumb is pointing to the right. So that means that it's being forced to move to the right, like that. Okay. That is the most complex part of my notes. Done. If you have questions on that, let me know. But now, like that's, I think that's enough room. I'm just going to briefly talk about Ampere's law. Now that we've covered all of this. I'll just put the formula down for it. We're not going to use this formula today, but I'll just have it up so I can reference it in my little definition. I'm going to say. So there's this version. There's also this version. They're both pretty intimidating to do. What it's saying is, again, I don't think we're not going to be using these today, but what it's Ampere's law is saying is that the magnetic field strength, let me write this down, magnetic field strength in a current carrying wire is proportional to the amount of current flowing through that wire. And that is Ampere's law. Okay, so let me zoom out like that. Any questions on the notes or the lab? Oop. I'm only looking for just any set of pictures that you're going to draw today. I just want to see that they're labeled correctly, like you label which side's north, label where the wire is, label the current direction. You don't have to draw magnetic fields for that first part. What else? Remember that there's quiz 3 out. So you could do that too. That, and let me get the breakout rooms up.